Hilchos Kiddush Hachodesh Perek Shneim Asar. The laws of sanctifying the new month, chapter 12. So before we start today, let's just remind ourselves what we're trying to accomplish here. Every day, all of reality is turning from east to west. That's why we see every day Zricha and Shkia, sunrise and sunset. The sun comes up in the east and the sun goes down in the west, because every day there's what's called the Galgal Hayomi. The Rambam says there's like an outer force outside all of reality that's turning everything from east to west. At the same time that this Galgal Hayomi is turning everything from east to west, the sun and the moon themselves are climbing the other way. Very slowly, they're climbing the other way from west to east. So if you're on a train, and the train is going east, and then you walk to the back to the bathroom, so which way are you going, east or west? Well, the train is taking you very fast this way, but you're walking very slowly a little bit this way. Same with the sun and the moon. Every day the sun and the moon are going very fast, from the east to the west. But slowly they're going west to east. And it's this slow movement that we're after in these halachot. That's what we care about. When we say we want to know where is the sun, where is the moon on the night of Rosh Chodesh, that's what we want to know. Where is the sun and the moon on their own little slow path? Because when we know where the sun and the moon are and how far they are from each other, that's how we're going to determine if we're going to be able to see the moon on the night following the Molad, and the night that could be Rosh Chodesh. So, the Rambam is going to spend now 2 chapters talking about the sun and how we define the accurate placement of the sun. And then the next 5-6 chapters are going to be about the moon, because the moon is a lot more complicated. What did we learn yesterday? Yesterday we saw that the planets go around the earth. For example, here's the sun. The sun is making an orbit. You see my mouse? Yeah. It's going all around the earth from west to east, this way. And so, if you're standing on earth, at any point, if the sun is over here, you're going to see the sun going out, and you're going to say, oh, it's over here. It's at 0 degrees. Then when the sun moves to here, and you're going to see the sun, you're going to say, oh, it's at 30 degrees. You're going to label the placement of the sun. However, the problem is that the whole orbit of the sun is off-center. See, the orange circle is the center of the sun's orbit. The earth is a little bit off-center to that. So what happens? Let me try to show you on this diagram over here. I'm going to only show you like more extreme cases so you can see the actual difference. Let's say over here, in this position, the sun is at 90 degrees. This is 90, right? 30, 60, 90. It's at 90 degrees on its orbit. If you count on its circle from 0 degrees, it traveled 90 degrees. But that's only 90 degrees if you're looking from this orange circle, from the center of the sun's orbit. Boom, 90. But if you're standing on Earth, while the sun is on the 90 spot, but you draw a line out to the stars, look what you're going to see the sun? 80 degrees. You see that? On your big circle, because this big circle is the main circle for the observers on Earth. That's how we identify movement of the planets against all the big stars. So while the sun on its own path is 90 degrees, you're going to see it behind at 80 degrees. That's in the first half of the circle. Let's do an example from the second half of the circle.
Because that's the only way we can identify.
Yeah, because we only have...
Only the little circle we can't identify.
Right. We don't have movement against it. We only have the other side. Look at the other side. Now the sun is at 270. Where's my mouse? Here. Sun is at 270 on its own path. You can't really see the numbers clearly, but that's only if you're looking 270 from here. If you're looking from Earth and you draw a line to 270, actually it's going to come out past 270. It's 280. Basically on the first half, you're always going to see the sun more behind, and on the second half, you're always going to see the sun more ahead. Now, this would be an easy enough problem to solve if that was it. How would you solve this problem? I would just give you a table. And the Rambam is going to do that tomorrow. He gives you an easy table. If the sun is at 10 degrees on its own path, you're going to see it at 8 degrees, let's say. If it's at 20 degrees, you're going to see it at 18 degrees. He gives you a table, and so now we'll be able to know. All we have to figure out is where the sun is on its own orbit, and we'll be able to make the adjustment very easily. Right? That would be if this was it. But there's another thing I have to throw into the mix over here. And that is that the whole circle of the sun is also moving. So right now...
3 movements.
Yes. Right now, 0 degrees is the furthest point from Earth, and 180 degrees is the closest point to Earth. Yes? But over time, very slowly this happens. Over time, look here, you can see this is called the Gova. Gova means the highest point. In English it's called the Apogee. Gova means the point on the sun's orbit that's most distant from the Earth. But look what happens here. Over time, the Gova moves. Now, the furthest point is 60 degrees. This is still going to call it 0 degrees because the point that's behind Taleh, Aries, is always called 0 degrees. But now the furthest point from Earth is over here. But what happens because of this? Now, it's not between 0 and 180 where you're going to see it behind, and 180 to 360 where you're going to see it ahead. Now it's from 90 to 270, or 60, here's the furthest point, I'm sorry. From 60 to here to 240, that's where you're going to see it ahead, and from 240 to 60 is where you're going to see it behind. So if you want to establish the accurate placement of the sun, you have to do two things. You have to first figure out where is the furthest point from the orbit relative to Earth, where is the Gova, where is the Apogee, and then you have to figure out how far away is the sun from the Apogee, and then you can use the table that the Rambam is going to give us tomorrow. In other words, wherever the Gova is, you're going to consider that to be somewhat 0 degrees. And you're going to say from this until 180 in the circle, you make the adjustment for the sun to be behind, and from the other half of the circle, from 180 to 360, technically, you're going to make the adjustment to be ahead. Okay? So just to summarize, there's two issues. Or really, let's call it three issues. We have to figure out where is the sun on its own orbit. That's an easy thing to do, because we know how often it moves every day, and that's happening every day at the same pace, steady. Then you have to figure out which point on the sun's orbit is the furthest from the Earth, and then you have to figure out how far did the sun get from that highest point to do the adjustments. But all the adjustments are going to happen tomorrow. Today, the Rambam just introduces us to these two concepts. The fact that there's a sun's orbit which changes relative to the perspective on Earth, and the fact that there's a point on the orbit which is the furthest from the Earth and how fast that moves. So here we go inside. Now it should be very easy. Just two halachot, we'll get through it.
Yeah. Why is that relevant? Why is the placement of the sun right now relevant to the moon?
Because what's going to define whether we can see the moon after sunset is how far it got from the sun. So we have to know where the sun is.
Why? I'm trying because it's blocking it.
No. So what happens is like this. Here's a circle, right? So you have the sun, and the sun is traveling very slowly, 1 degree per day. Yeah. The moon is traveling 13 degrees per day, much faster. So after a month, it catches up to the sun, right? The second after it catches up, it continues moving eastward. Right? So the moon, yeah. So every second it's getting further and further from the sun, eastward. But reality is being pushed westward. The sun is being pushed to set on the horizon every day. So now, right after sunset, the moon is a little bit further east from the sun. It hasn't set yet. That's the window that we have to see the moon. But only if it got far enough from the sun to be seen. The sun is super bright. If it hasn't gotten far enough from the sun, we're not going to be able to see it. So we have to know where the sun is, where the moon is, how far are they from each other, and then we're going to know. But in order to figure out where the sun is, we have to know where the sun really is. And that's what the Rambam is going to be after in today's and tomorrow's chapter, to define.
In layman's terms, does that mean that we have to know when sunset is?
No.
That's nothing to do with
sunset. We're going to know automatically when sunset is. We have to know. We have to know how far the moon will be from the sun at sunset.
And why is that relevant? I'm sorry to keep on.
Because.
How do you measure the place of the sun and the moon?
Either we can see it or we can't.
Yeah. Hold on.
Either we can see it or we can't.
Right. So, but how do we know if we can? In other words, when are we going to be able to see the new moon? When is that window? When there's no sun. Right? There has to be, because otherwise the sun is in the sky. You can't see the moon.
It's too much.
I mean, you could sometimes during the day, but only when it's a full moon. When it's a tiny little moon, you can't see it if it's in the sun. So you have to wait till right after sunset, and that little window when the moon is still in the sky, because remember the moon is moving eastward, away from the sun. So let's say it got here. So here's the horizon. Sun sets. Now you have this little chance before reality pushes the moon also down, below the horizon. That's your little window to see the moon. The question is,
this only happens with Hachodesh,
right? Because during the full moon, it's all the way over here.
Right.
That's why the full moon comes up in the sky. Like tonight, it's a full moon. We're going to see the moon so geschmack because it's right in the sky.
You missed that point. That
it's only this time. Yes, of course.
That
Okay. That was. I took it for granted. I should have explained that. Okay, so let's see inside. Halacha Aleph. Mahalach hashemesh ha'emtzai b'yom echad shu arba ve'esrim shoyes. The rate of progress, the distance that the sun travels in one day, meaning 24 hours. And he uses the word emtzai. Emtzai means the one on its own orbit. We don't care about how the earth sees it. Just if you were measuring it on the yellow ball, how fast is the sun traveling every day? Tisha v'chamishim chalakim u'shmeina shniyos. 59 minutes and 7 seconds. These are minutes of space. Again, it's just under a degree, because each degree is 60 minutes. So it's 59 minutes and 8 seconds. Almost, we're just going to call it a degree per day, okay? Almost a degree per day. Simanam chavdalid nun tes ches. Chavdal means 24 hours. Nun tes, 59 minutes. Ches, 8 seconds. Nimtza, so if you do the math, mahalacha ba'asara yamim, in 10 days, how far does it travel? Teisha mailis, ve'echad v'chamishim chalakim, v'shalosh v'esrim shniyas, 9 degrees, 51 minutes, and 23 seconds. Simonam, the Rambam always gives it into numerical value. Tes, nun aleph, chav gimel. 9 degrees, 51 minutes, 23 seconds. V'nimtza mahalacha b'mea yam, if you go 100 days, it comes out to be shmeina v'tishim mailers, or shleishosh leishim chalakim, v'shalosh v'chamishim shniyas, simanam tzadik ches lamed gimel nun gimel. 98 degrees, 33 minutes, and 53 seconds. V'nimtza, and it comes out, she'eris mahalacha be'elef yom, the remainder of its walk in 1,000 days. He uses the word remainder because achar shetashlich kol shloish meis v'shishim mailes k'mei shabiyarnu. After you throw away each 360. In 1,000 days, it travels 1,000 degrees. But on a circle, it's 360 degrees, you're back to point zero. So you don't care about every 360. So in 1,000 days, how much practical progress, net progress, will the sun make on its orbit? Masayim v'chamish v'shishim mailes v'shmeina shleishim chalakim v'chamishim shniyos simonam reish samachei lamed ches nun. 265 degrees, 38 minutes, and 50 seconds. The remainder, in other words, the net progress in 10,000 days is 136 degrees, 28 minutes, and 20 seconds. Using this math, if you know the amount for one day, if you're feeling like making funny numbers, 168 days, how many times? Just do the math, and you'll get to the number. By the way, the commentaries point out that if you do the actual math, as the Rambam says it, it doesn't actually equal out. If you use 59 minutes and 8 seconds, times it by 100, it isn't going to come out to exactly the number that Rambam gives. And that's because, really, the Rambam had a much more exact number. There's seconds and thirds and fourths and fifths. And if you combine those accurate numbers, you get to the total numbers of 100 days and 10,000 days, etc. If you want to make your own signs, so it will be known to you for how much the sun progresses. 2 days, 3 days, 4 days, 10 days. Tasa, you can do. If you want to know signs that will be ready for you, for your knowledge, for how much progress it makes, 20, 30, 40 till 100, Tasa, you can also do. How does it work? It's actually obvious and super easy to know. Once you know how much it makes in one day, you just keep on adding, and that's how much it makes in whatever days you want to have. The Roihu, now the Rambam says, I've given you the numbers for 1 day, 10 days, 100 days, 1,000 days, and 10,000 days. But for these halachot, it's actually very fitting that you should always know, liyos muchan v'yadua etzlecha, mahalach emtza hashemesh, l'tisha ve'esrim yoim, v'lishloish me'es arba v'chamishim yoim. It's important to know how fast the sun progresses every 29 days and every 354 days. Why are those numbers important? Shehen yemei shnas halavana, bizman shachadosh kesidron, v'ya nikras shana sedura. It's the days of a full lunar year, when the months are in order, 29, 30. It's called a shana sedura, an orderly year, 354 days. Plus, of course, 29 days is a lunar month. So you want to know how fast the sun progresses in that time. Because if you have these mean rates of progress, these average progresses ready to go, it'll be very easy for you, or easier for you, to calculate the sighting of the new moon. Because there's always 29 full days between one night of sighting and the next night of sighting. And in every month, there can be no less than 29 days. No more means no less than, no more less. In other words, you can't have less than 29 days. So therefore, it's good to know how fast the sun moves in 29 days. Because all we care about, again, we're not learning astronomy. We're learning astronomy as it relates to the halachot of seeing the new moon. So that's all we care about. Will the calculations lead me to seeing the new moon? Same thing if you want to calculate from year to year on a certain month, from Nisan to Nisan, from Tishrei to Tishrei. So it's always going to be from the night of sighting on 1 year to the night of sighting the same month the next year, Shana Sedura or Shana V'yam Echad will be either an orderly year, 354 days, or maximum a difference of 1 day, 353, 355, V'chein b'chal Shana V'shana every year. So if you have those numbers, it'll be easy for you to calculate month to month or year to year. So what is that number? The mean rate of progress that the sun makes on its own orbit every 29 days is Shmeina ve'esrim mailes v'chamisha shleshim chalakim v'shniya achas simanon chavches lamed hey Aleph, 28 degrees, 35 minutes, and 1 second. Its progress in a year that's orderly, 354 days, is shleish meis or shmeina v'arba'im miles v'chamisha v'chamishim chalakim v'chamisha srei shniyos simanon shin mem ches nun hey tesvav, 348 degrees, 55 minutes, 15 seconds. That's all the sun's progress relative to itself. Now that Rambam introduces the second point that I told you. Halacha beis, nekuda achas yesh begalgal hashemesh. There's always one point on the sun's orbit, v'chein b'shar galgal hashiva kechavim, and also on all the other 7 planets, but we only care about the sun today. And that point, be'es sheyiyah hakoichav ba, when the star, in this case the sun, is found on that point, yiyah govaya me'al ha'aretz kol me'oiroi, or some texts have kol me'oidoi. It's going to be the highest from Earth. Its light will be furthest, or its strength will be furthest from Earth. Right? So in the case that I showed you before, we're going to go with the regular chart. This is the Gova. Okay? The apogee. And the Rambam says, "V'oisa hanekuda shel galgal hashemesh u'shar hakechavim," and that point of the solar orbit and all the other stars, chutz min hayareach, besides for the moon, this is very important. The Rambam clearly says that the moon's orbit also has an apogee, but it doesn't move. Soiveves b'shaveh, it moves steadily. In other words, you have to always know where is the furthest point, because the furthest point is always changing. And its progress is super slow. Okay, about every 70 years, it moves about 1 degree. This point we're going to call the height, the apogee of the sun. How far does it move in 10 days? It's nothing, okay? It's a second and a half a second, 30/3. We're talking about a 60th of a 60th of a degree. In 100 days, how much does it move? Just 15 seconds. A quarter of a 60th of a degree. In 1,000 days, it's over 3 years now, or just under 3 years, it moves 2 minutes and 30 seconds. Even in 10,000 days, it hasn't even moved half a degree, 25 minutes. For 29 days, which we do care about every month, about 4 seconds and some. In a proper year of 354 days, 53 seconds, that's how far it travels. Okay? And again, why is it going to be important to know how far this Gova travels? Because that's going to indicate the adjustment we have to make for the proper placement of the sun. Only once you know what's the furthest point of the sun from Earth can you know how much to adjust from the perspective of the Earth's observer. But again, those adjustments are going to be made tomorrow. Today, the Rambam is just giving us the facts.
When you say Yerushalayim?
Yes, of course. Yeah, I mean only Yerushalayim. Okay, now that Rambam, as he always will do, will spend considerable time visualizing what he just said relative to his time. Kvar amarnu, we've already said yesterday, sheha'ikar shemimenu haschalas cheshbon zeh. At the starting point from which we always begin all calculations in this instance, hu mitchilas leil chamishi sheyom shlishi l'chodesh Nisan mishnas shmeino shleishim u'sham meis v'arba'as alafim liyitzira, is the night of Thursday, Wednesday night, going into the 3rd day of the month of Nisan, year 4938 from creation. So, because that's the starting point, I have to tell you where are all the planets in the starting point. The placement of the sun on its orbit, on the average walk. At this starting point, it was b'sheva miles u'shleisha chalakim u'shtayim u'shleishim shniyos mimazal taleh. Simanon Zayin Gimel Lamed Beis. It was at 7 degrees, 3 minutes, and 32 seconds of the constellation of Aries. Remember, it's the month of Nisan now. So of course, the sun is going to be at the beginning of its walk. Where's my mouse here? Oh, this is 0 degrees. The sun was about 7 degrees, right over here. On the 3rd day. On the 3rd day of Nisan, at the starting point. Where was the height of the sun? Where was the apogee? At this starting point, it was 26 degrees, 45 minutes, and 8 seconds into Gemini. So, I actually think in the picture that I showed you, it was pretty accurate to that. Okay, not exactly, but you can see the point is already further from 0 degrees. The highest point is already in the constellation of Gemini. Actually, it was about here. 26 degrees into Gemini would be about 86 degrees. That's where the highest point was. with all the little numbers, 45 degrees, 40 minutes, 8 seconds. So now, if you want to find out, you're in 5784, so over 800 years later, you want to know where is the sun on its average orbit. Anytime you want, just count from the starting point. How many days have passed till the day which you desire? And you will be able to achieve, to get the amount of progress that it's made in those days, based on the signs that I already gave you. Add it all to the starting point. Of course, add the seconds to the seconds, minutes to the minutes, degrees to degrees. And whatever results is the placement of the sun on its average orbit for that day. Let's apply it practically. How would this look like? We know where the starting point is, and we want to find out where is the sun going to be. A couple of months later, Friday night, 14th of Tammuz, from this year 4938, the starting year. The number of days from the starting day until the beginning of the day, which we want to know about, Friday night, 100 days. Well, we know how much 100 days it progresses. We take the progress for 100 days, 98 degrees, 33 minutes, 53 seconds, and we add it to the starting point of Shu Zayin Gimel Amid Bey, 7 degrees, 3 minutes, 32 seconds. The resulting calculation is 105 degrees, 37 minutes, 25 seconds. So the placement at the beginning of this night, or Friday night, where was the sun in its average orbit? The Mazel Sarton, 15 degrees into the constellation of Cancer, 37 minutes into the 16th degree. Now, a very important caveat. The placement that you get using this calculation is supposed to bring you to the beginning of the day. Yes? It tells you if every day, every 24 hours, the sun progresses this much. So if you go 100 days forward, you're getting to day 100 at the beginning of the day, which we're calling 6 p.m. Because every day in halacha is just 24 hours, 12 hours night, 12 hours day. The problem is that we know sunset is always changing. Sometimes it's at 6 p.m., yes, but sometimes it's earlier or later. So the Rambam says, the placement that you're going to get using this calculation, yes, sometimes it'll come out that that's the beginning of the night, exactly. But it could actually be anywhere between an hour before or an hour after sunset, depending on the time of year. So, let's say if I want to know where the sun's going to be Friday night, and I get the calculation, but yeah, that's no good for me because the sun is going to be an hour before sunset in Tammuz. I need to know where is the sun going to be in another hour, when it's actually sunset, when the sun goes down, and that's when I can see the moon. So the Rambam says, don't worry about it. When it comes to the sun, don't worry about it. We are going to make an adjustment for this. We're going to compensate for this when we deal with the moon. At the end of chapter 14, the Rambam will give us the adjustment for this, exactly to figure out whether you're in winter or summer, how to adjust the timing for sunset in your location. But that's just a side point. Back to the main thing. Using this calculation, you can go with anything for whatever time you want. Even if you're 1,000 years later. This is the Rambam in 4938. In 5938, you can use the same calculation and get the sun's placement. Gather together all the remaining numbers, add it to the starting point, and you will get the average placement of the sun on its own orbit. And the same you can do with the average position of the moon and the average position of every single planet. Once you know, and you got to trust me on this, the Rambam says, once you know how much it progresses every day, and you know the starting point, and where the sun was at the starting point, or the moon or the other planets, and you'll gather all the progress for all the days and years that accumulated, you add it to the starting point, you will achieve its placement in the average orbit. Same thing you can do with the apogee of the sun. Taisif ma'aloche ba'isam ayamim me'ashanim alo ikar. You know the starting point. Add the progress for whatever amount of days that you want. You will achieve, you will get the result of the placement of the apogee of the sun for the day that you want. Now that Rambam says, I understand, I'm writing this book in 4938, there's going to be hundreds of years, and we're going to be in Sherman Oaks studying this Rambam, 800 years later. And it's going to be very tedious to make all the calculations back from 4938. So the Rambam says, if you want to make your own starting point that you can start from, outside of this starting point that I have given you in this year. You want to have it at the beginning of a certain cycle or the beginning of a certain century. You have the permission because you can do whatever you want. Once you know the math, it's just simple arithmetic. And if you want to make the starting point even before, you don't like 4938, you want to go back to 4000. Yeah, good for you. Or after, also fine. The path is open. What's the path? You already know the progress for a year, for a month, for a day. And we also know all lunar years are 354 in an orderly year, or a little more, if both Cheshvan and Kislev are full, or one day less if they're both lacking. A leap year, you also know how to calculate. Im yu chadashah kesidran tia yesed ala shana hasdura shleishim yaim. Vim yu chadashah shleimim he yesed ala hasdura echad shleishim yaim. Vim yu chadashah chaserin he yesed ala hasdura tisha v'esrim yaim. A leap year is either 29, 30, or 31 days more than a regular lunar year. Since you have all these principles known, all you have to do is just figure out the progress for any year and day that you want. Add it to the starting point if you're going forward. You'll get the average placement for the day that you want in the future years. And make that day the starting point. Or you subtract it from the starting point that we've given you. And you will get the starting point for the day that you want from the days that have passed. And make that day the starting point, that place starting point. And assuming you know the progress for one day for any other planet, you can do the same for all the planets. And also, from everything we've said, it's already clear, of course, same way you can calculate a future date of the placement of the sun, so too you can figure out the placement of the sun in days that have passed. Just work the opposite way. Instead of adding, you subtract.